This lecture is going to be on the topic of kinetic molecular theory, and looking at the title, if you sort of break that down, a theory is an explanation for some observed properties, and we're going to be talking about molecules in motion, so kinetic being motion. Here are some of our key concepts. First, we're going to go through some of the major points of kinetic molecular theory, some of the major tenets that underline the theory. We're going to look more specifically at three states of matter, including the similarities and differences in the three main states of matter being solids, liquids, and gases. Finally, we're going to be looking at this concept of average kinetic energy, what that means in terms of particle motion, and then how that corresponds to the temperature of a substance. So, getting into some of the major points. Kinetic molecular theory is, of course, a theory being an explanation based on observed data. Now, the theory is based on an idealized set of data. It fits the vast majority of the data that is measured about solids, liquids, and gases and how those particles move. There are some temperature ranges where the theory breaks down and doesn't match the data, but it is a very good model and fits most experiments that are done. Some of the major tenets, these main ideas, there's really three main ones, and then there are some others. The one being that particles are always in motion. So even though you might look at something like a solid, like say a desk, and it looks like nothing is moving, you can actually, if you got in and zoomed in far enough, you would see that those solid particles of the desk are in motion, and we'll look at some animations of that. You'll also note that particles move in random directions. So there's a randomness to it. They bounce off of each other and move. They're sort of like billiard balls in a way, or pool balls moving around, kind of bouncing in random directions, bouncing off the walls of their container and off each other. Something you'll also note, as particles do collide, they often interact, and that's where some of the data breaks down, especially when it comes, or some of the theory doesn't match the data when it comes to gases, but the closer the particles are, the more likely they are to collide and interact with each other, whether it's a chemical reaction or just some sort of electrostatic positive-negative attraction. And so now what we're going to do is look at some animations of particles in motion, and we're going to look at a few solids, liquids, and gases. And first, looking at solids, we'll get to the animation in just a moment. Solids, in terms of particle motion, is pretty limited. You'll see that they are pretty much stuck in place, and the term is actually, they kind of just vibrate back and forth, and you'll see that. In terms of particle density, comparing solids, liquids, and gases, these are the most dense state of matter, solids being more dense than liquids. There are some exceptions to that, which I'll address. And then in particle attraction, so that would be like two adjacent particles. How much are they attracted to each other? They have the most attraction in solid compared to the liquids and the gases. The attraction or the interaction is the strongest. This animation you can find at preparatorychemistry.com. It's a flash animation. You can see it's copyrighted by Mark Bishop, so this is not my animation. I just wanted to make sure I don't take any credit for it. But what you're looking at here are particles in a solid. You can see that they are fairly packed in place, pretty closely aligned. Now they're not in motion right here. This is just to show some of the arrangement. When they're in motion, they tend to not be quite so orderly. And so now what you can see as it's going, this is still a solid, but the particles are in motion. And you can see that they're kind of just moving back and forth, not too much. I think it's easiest to spot that one that's sort of a brown color, and just watch how it's moving around. It's just kind of bouncing around in its little area. It's definitely colliding a lot, and it's interacting with the other ones. If they were different molecules or different substances, there might be the opportunity for a chemical reaction, but you can see they're in very close quarters, and you can see why the density is so high. Liquids, on the other hand, they have some similarities to solids, but also some key differences, and so we'll highlight that. In terms of particle motion, it's somewhat limited. It's often called a flowing motion. If you ever, or if you can imagine having a glass of water and you put some food coloring in it, you can see the food coloring kind of move around and then get mixed up. Those particles are in motion, even though maybe you can't see it. But again, it's a little bit more free than liquid or than solids, but not as packed in place. They have more freedom to move. Density. The liquids tend to be less dense than solids, and there are some exceptions, water being one. Ice floats on water, right? So that would be a solid ice being less dense than the liquid water. That's pretty rare, but that's one of those reasons why water is kind of a special molecule. But your general rule is that solids are more dense than their liquid counterparts. In terms of particle interaction, they are of course going to have a lot of chemical reactions are going to be occurring in liquid or aqueous states. But again, being that they're not quite so densely packed in there, those particles are probably going to interact less compared to solids. Returning to the animation now, you can see this is a liquid. The density, the particles are still pretty dense in there, although there is more room. They are moving around more. At least more freely. You can see that brown sample that we're looking at. It's not just kind of trapped in its little prison. It's bouncing around a lot more, sometimes going off the screen. So you can see again a flowing motion, less density than solids, and significant particle interaction. I don't mean to imply that solids have so much more particle interaction, but just in terms of density, they're going to be bouncing around more frequently. But you can see there's still ample opportunity for these particles to interact and potentially react with one another. The final state of matter that we're going to be examining with regard to kinetic molecular theory and particle motion are gases. Gases are significantly different than solids and liquids in a few ways. Their particle motion, they are the most free by far. And the reason for that is density. Gas particles are way more spread out. You can try and punch your hand through a desk and see how that goes. You could also try and punch your hand through the air. Particle density will tell you which one is more or least dense. So because they are, again, so much less dense, the motion is very free. They can move around. There's a lot of time where a particle won't be colliding with any others. So that would of course mean that particle attraction or particle interaction is going to be the least. The gas particles, they do collide. There can be reactions in a gaseous state. There's lots of them actually, but it's just a little bit less frequent because again the particles are so much farther apart. Having a look at these gases or these particles now, you'll see a significant difference. I think solids and liquids looked very similar. The densities are pretty close in solids compared to liquids. Gases significantly different. A lot fewer particles in the same space of area that we're looking at. What you'll note is fewer collisions. Now they are still colliding, and you'll see that, but there's fewer compared to in the same area of space. There's just going to be fewer collisions. You can see that they're bouncing off the walls. That's called pressure, and we're going to be looking at that in a subsequent lecture. But as those gas particles bounce off the walls, they exert a pressure, and you can see freedom of motion. They do kind of have that billiard ball look to them, just bouncing around, interacting somewhat frequently, but their interaction is definitely less than solids and liquids. Taking a last look now at motion of particles and relating it to temperature, as I said here, we need to look at probably something that might be a new concept, is average kinetic energy. Okay, so average is meaning you're taking all of the particles together. Kinetic energy is the energy of motion. It's simplified. It's not quite this definition, but what you're looking at is the average speed of the particles. It's how fast the particles are moving. So a higher average kinetic energy means they're moving faster. a lower average kinetic energy means that the particles are moving slower. And I say it's not a perfect definition because kinetic energy actually also incorporates the mass into multiplied by the velocity squared, and that gives you a little bit more of a sense of the kinetic energy, because obviously something bigger moving at the same speed is going to have more energy to it. But again, because particles are so small, for our purposes in this class, we're looking at really just relating kinetic energy to speed. Now, that's temperature. Temperature, we have a everyday understanding of it, meaning, how hot it is outside or how cold it is outside. But a more mathematical, a more really physically based understanding is the temperature is a measurement of the average kinetic energy or the average speed. So we can use those close to synonymously. Average kinetic energy equals the speed, and that also equals the temperature. And taking a look again at our animation, you're looking at a solid again. And so again, note the particle density, note the interaction and all those collisions. But now we're going to look at it in terms of temperature. So again, temperature being the average kinetic energy or the average speed of the particles. Just take a look here at roughly how fast the particles are moving. And now what I'm going to do is crank up the temperature on this animation. And you can see they're moving faster. So how did we turn up the temperature? Maybe you supplied some heat, whatever it was, but adding temperature to the substance makes the particles move faster. So you can see there's a little bit more rapidity to what they're doing. So I'm going to go back to a lower temperature, and now again a higher temperature. And so you can see the relationship still in a solid, that as you heat them up they move faster. And so putting it all together here, with increases in temperature, the substances tend to get more disordered. And the reasons for that are in a way kind of complex, but what happens is they get more energy, which allows them to spread out a little bit. The particles don't cram in together to have those nice, strong intermolecular interactions. And so as you increase temperature, the same substance, and we'll take water because it's the easiest one to relate to. Water starts as a solid at low temperatures, and then if you increase the temperature, the particles break their intermolecular hydrogen bonds and become a liquid. And then if you continue to heat it, increasing the temperature, the particles speed up more, move faster and faster and faster. The liquid, again, those particles are moving quick, and then at some point they begin to vaporize and go from a liquid into a gas. And so that transition of solid liquid to gas, the temperature will increase for the same substance as you go along. And so here's our recap of kinetic molecular theory. The basic idea is that particles are always moving, and they're always moving in random directions. Those three states of matter, they have different particle spacings and interactions, depending on whether it's a solid, liquid, or a gas. And then finally, temperature measures particle motion, and that is average kinetic energy. And so you'll want to have an understanding of those three main concepts, and that's it for this lecture.